All right, 8.3. I know it's a little late, but better late than never. I know I skipped 8.2. It was super short, and all of it could have been explained just by using your notebook. Just read through that, and you'll understand. Okay, a new figure. If we take an image or a figure and we move it somehow, the unmoved image is the pre-image, and once we move it, we call it the image. We've discussed this before in class. Figures in the plane can be reflected, rotated, dilated, or translated. The new figure is called the image. Once we move it, once we reflect it, we call it the image. Okay, the line of reflection, that's for a reflection, okay? If I have here the pre-image, and then I reflect it over the line, I get my image. Pre is like prefix, it comes before the word. Pre-image comes before the translation, or reflection, or whatever. When a figure is transformed, the original figure before the transformation takes place is called the pre-image. Dilation is sometimes referred to as enlargement or reduction. A rotation is usually we refer to it in counterclockwise. All of your rules that we're going to use in class deal with counterclockwise rotations. We always rotate around the center or the origin. Sometimes it's called a turn. Now what's interesting is a 90-degree counterclockwise rotation is the same thing as a 270-degree clockwise rotation. It's the same thing. Think about it. If you turn right, that's a 90-degree turn to the right. It would take 3 left turns to make the same as a right turn. Hopefully that helps all. So 180 degrees is the same both directions. 270 counterclockwise is 90 degrees clockwise. Again, same thing. 3 left-hand turns, so left, 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 is the same thing as just 1 right-hand turn. All right. Notice how the distance from the center of rotation is preserved. This distance here is the same as this distance here, and the degree of rotation is 90 degrees. Translation. It's also called a slide or a glide. Nothing changes, just the position on the map. Moving from here to here. A reflection has to have a mirror line or a line of reflection. The pre-image is then flipped over that line like a pancake. Also called a flip or a mirror, but technically is a reflection. The operation that maps or moves a pre-image onto the image is called a transformation. Now, in algebra, we talked about this concept of f of x. And if f of x equaled 2x plus 3, then we would have this kind of a scenario of, if I put in a 5, I'd get out a 13. It takes a function, takes some value, mangles it, mashes it, mixes it around, and spits out a new number, a 13. Okay? So, these transformations that we're talking about here take a point, x, y, and they mangle and mash them up and mix them out, and they spit out some new number. Maybe it's going to be negative y, x. Who knows? The point is that it's just like a function. It's an operation. It takes some point, xy, and manipulates it to be something new. All right. So an isometry is a very specific kind of transformation that preserves length and angle measures. All right. If we look at rigid motion transformation or rigid transformation, it's just another way of saying isometry. These 3 concepts, congruence transformations, rigid transformations, and isometries, are the same thing. They all preserve distance, lengths, and angles. So if we look at this as which one is not a rigid transformation or which one is not an isometry, the answer would be a dilation, because the distances aren't the same. Notice how this distance from top to bottom is bigger than this distance from top to bottom. So it's not an isometry. Okay, so now how do you identify if it's an isometry? You got to look and see if the distances are the same, if the angles are the same. Okay, if you can preserve distance and angle, then you're fine, or if the shapes look identical. What are the 3 types of congruence transformations or isometries? We have reflection, translation, and rotation. A reflection is a transformation that acts like a mirror. Okay, so every single reflection has a line of reflection. Okay, Notice the smiley face here. It's curved this way on this side. Then we reflect it and it's curved the opposite way, as though we were looking at it in a mirror. All right, so the line which we reflect is called the line of reflection. So vocabulary word, we call it the line of reflection. Notice this interesting scenario here. P is the same distance away from the line as P prime. They're the same distance away. It's also 90 degrees. Okay, so it's called a perpendicular bisector. We talked about this back in the beginning of the school year. But a mirror image or a reflection has to be perpendicular and the same distance away from the line of reflection. All right, so it's an isometry. So right here, reflection theorem. A reflection is an isometry. So which is true? A reflection is an isometry. It just said it right up here. It's not a rotation. It's not a transcription. That's not even something we've talked about in this class. We don't even talk about transcriptions. So it's got to be an isometry. All right, there are three methods for doing reflections. Graphing can be the simplest. If I don't give you any points, I just show you a picture of this, you've got to be able to reflect it over the x-axis. Okay? If for the coordinates, it's different, but for the graphing, you just have to count the distance away. I'll show you that later. But for the coordinates, there's a rule that says if I give you a point, AB, you manipulate that point into becoming A negative B. Okay? So if we look at it as a matrix, the point AB is just a 2x1 matrix. X is on top, Y is on bottom. It becomes A on top, negative B on bottom. So you just change the signs of all the Y values and you're done. We're not going to worry about matrix multiplication because for a reflection, it just is silly. You just don't do it. So if we reflect over the y-axis, notice how we're going from here. We count the distance to the y-axis. We count that same distance to here. But if we give it a coordinate, AB gets mangled and mashed up and gets spit out as negative AB. And again, as a matrix, X is on top, Y is on bottom. It becomes negative X's. The Y's don't change at all. And again, we don't look at reflection matrix because it doesn't make any sense. So if I reflect over this line here, Y equals X, I have AB is reflected over the line Y equals X. Here's the rule we follow. Again, AB gets mangled, mixed up, and spits out as BA. We just switch places. So as a matrix, it says A over B becomes B over A. There's your rule. Y equals negative X, same concept, only now we switch places and they've changed signs. So it was A over B, now it's negative B over negative A. And by negative, I mean change the signs. Reflecting over the x-axis, we've got a couple different options. I want to show you graphically how to do this first. Here's the x-axis in nice big blue. Now, I count to the line, 1, 2. And then I count again, 1, 2, and there's my point. So I have to look at how far away from the line of reflection I am. The point is 2 above the line, so I have to have my reflected line be 2 below it. I'm over here, this one's 5 above the line. I have to go 5 below the line and connect the dots. 2 above, 2 below. I draw my line, and I'm done. I had successfully reflected this shape over the x-axis. Now, to do it again over the y-axis, notice my blue line now is my y-axis. I have to say how far away from it am I from the blue line? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Very nice. 5 to the left, 5 to the right. Same up here, 5 to the left, 5 to the right. I connect my dots. Now this guy, he's on the mirror. He's on the line, so he doesn't move at all. Leave him alone. If you're on the line of reflection, guess what? You reflect onto yourself. So when I reflect over this line here, we've got a couple different options. I want to show you visually what we're doing. Remember how I told you we have to be perpendicular to the line of reflection? So if I count diagonally one step, and then I count another one to here, then I've got perpendicular lines, and I've counted the same distance away. So 1, 1. And it's 90 degrees, and that's how I'm going to find that point. Now, also, I would recommend you use the coordinate rules. So we say, find the coordinate. The coordinate of our first vertex is a negative 5, 2. Now, according to the rule, we have to switch their locations, right? So negative 5, 2 becomes 2, negative 5. That's the rule for switching over the line. Negative 5, 5 becomes 5, negative 5. And 0, 2 becomes, this is written, it's 2, 0. Okay? And then I connect my dots, and this is still 2, 0. Ignore that. All right. So if you'll notice, diagonally speaking, if I go 1, 2, 3 and a half, 1, we'll see a half, 1, 2, 3 and a half. Notice how they're in the same spot, and I traveled diagonally to be able to find those spots. Okay. All right, how do you reflect over the line y equals x? Again, you just switch the coordinates. Right there, switch the coordinates. All right, so we go through here. It's on your cheat sheet. All of these rules are right here on your cheat sheet for how to reflect. And then also we have a new situation. What happens if I give you a vertical line that is not the y-axis? It's going to look like x equals some number h, and y equals some k, some number k. Here I have x equals 2. Well, I told you it's a vertical line at x equals 2. So I find x equals 2 and I draw my line. There's my vertical line. Same rule. I count 1 to the left of the line, so I go 1 to the right of the line. 3 to the left, 3 to the right. 3 to the left, 3 to the right. I connect my dots, and there's my picture. The process is the same. I go left 1 to get to here. So I start at the same point. I go left 1 here. I like to start at my point and go 1, 1. 1, 2, 3. 1, 2, 3. There it is. That's how I like to do it. Now we look at the line y equals negative 1. Again, this is a horizontal line. Right here, horizontal line. Notice. So I draw a horizontal line at y equals negative 1. Please draw this line on your notes. Make sure you know what we're talking about. And then I count the distance to the line from any point. Well, that's 2 below, so I got to go 2 above. 2 below, 2 above. Now this one here is 1 above, so that means my new point has to be 1 below. I connect my dots, and there's my reflection. Perfect. All right, so now I reflect over the line y equals negative 1, or x equals negative 1. Again, x equals negative 1. It's a vertical line. I count how far away I am. I count the same direction, the other direction. So there's 1 to the left, 1 to the right. 1 to the left, 1 to the right. I connect the dots, and I'm done. So coordinate rule. This is the most reliable. It's most precise. The graphing method can also be really easy if you know what you're doing. They're all right here. Those are the rules that you need to use. They're going to be there for you on the test. So just know how to use them by doing your homework. Okay, there's your basic rules. So what are the coordinates of A prime after it's reflected over the x-axis? First, A is negative 4, 3. So I use my rule for x-axis to say AB becomes A negative B. A stays the same. It doesn't change. So negative 4 stays negative. Now notice B changes the sign. So 3 becomes negative 3. And there's my new point. Easy enough. So for B, I notice that my coordinate is 4, 3 for B, over 4, up 3. Now, the rule for the y-axis is it's negative A, B. So I say A changes the sign. That means 4 changes the sign, B stays the same, 3 stays the same, and I'm done. The answer is negative 4, 3. All I had to do was apply the rule for how to change over the y-axis. Now, D reflected over the line y equals x. Let's find the rule for what it is. Our value of D is negative 4, negative 3. And the rule for y equals x is AB becomes BA. Negative 4, negative 3 becomes negative 3, negative 4. Just swap places. What is the image of AG after it's reflected on the y-axis? AG. So I reflect A. I count 1, 2, 3, 4. 1, 2, 3, 4. A lands on B. So AG is going to become G or BG. Okay? You'll see it. 4 to the left, 4 to the right. G is on the y-axis, lands on G itself. So AD is the same thing as BG once it's reflected. Okay. The order is important on this one, by the way. If you start with A and B, and I ask you what's their image, then A has to start with B, so it has to be BG. So quadrilateral, KFHD. Let's see, there's the quadrilateral. Make sure we know what we're talking about. Now I want to reflect it over the y-axis. So I draw my line of reflection, and I say K. What does K reflect onto? J, good. So then I say, what about F? F stays the same, it's on the line. So I say JFHC. Got to be in that order. So graphing method is good. Matrix multiplication, I told you we're skipping matrix multiplication because it's so long that you don't even need to do it. Just make sure you write down these coordinates in your matrices. Okay, don't forget x's go on top, y's go on bottom. Okay, when we use matrices for matrix multiplication, you got to do row by column. And I give you the reflection matrix multiplication right here. Again, I'm telling you, do not use it. It's a long list of time wasting. It's cool that we can show matrix multiplication here. We're doing over the y-axis. So we say reflect over the y-axis. Okay. Matrix multiplication. First row, first column. -1 becomes a 1. 0 times 3 becomes a 0. It gives you 1 plus 0 gives you 1. Now, I told you this is a long, lengthy process, so I'm going to fly through it. -1, 4. -1, 4. 0, 4. -1, 2. 0, 0. Gives you -2. Notice how the -1 ends up being multiplied by the top value every time. And the 0 gets multiplied by the bottom value every time. So the 0 kind of makes this whole bottom row go away. And all that does is take -1 times the top row. Well, -1 times anything changes the sign of it. So really all I did was change the sign of the top row. And then on this one, notice how it's a positive 1. So the 0 still gets multiplied by the whole top row and they all go away. And anything times 1 is itself, so it never changes. 3, 4, 0. Never changes. So instead of doing matrix multiplication, I suggest you just do the coordinate rule. And notice that the top row changes sign when we multiply by the y-axis. Please plot and graph your new points on your notes. I will be grading it. You know what the points are here. You can graph it on here. You're good to go. That's from lunch. I had a little joke about that. How do you choose? How do you choose which one to use? Graphing method can be simple, but it can also be tricky. Coordinate rule is nice because it's very reliable. And matrix multiplication, in this instance, just isn't a viable reason. So, most transformations have 3 methods to solve the problem. Each transformation has a method that is the easiest. For the homework, you got to do the specified method, unless it's matrix multiplication. I've told you, you don't have to worry about it. If no method is specified, use the method you prefer. So for this one, it says find the image matrix. It doesn't say do matrix multiplication, but it does say it wants the image matrix. So I prefer using the coordinate rule in matrix form. Okay, so this is still just xy becomes negative b over negative y, a. So here's my whole matrix. Here's PQRS written in matrix form. Watch what happens. B becomes negative b on top. So I take the whole top row as a, and it becomes changed sign on the bottom. Take the whole bottom row, change signs, put it on top. There's my new shape. It took me all of like 3 seconds. Okay, the whole top row changes signs and goes on bottom. The whole bottom row changes signs and goes on top. Graph my new point. Look how pretty they look. And it is a true reflection. There's my line of reflection, and I can see that it's the perpendicular distance. It's beautiful. Okay, lines of symmetry. We know what lines of symmetry are. They're lines that make a map onto itself. Okay, so this butterfly, if I took this wing over here and I folded it over the line, it would land on top of itself. Think of some examples in nature that have lines of symmetry. Butterflies is obviously one of them. Looking into a lake, you can see the reflection of the mountains in the lake. Different types of bugs, faces of animals like a deer face, stuff like that. summarize what you learned today. Here's the calendar for next week. Pause it on that slide if you want to look at it some more. You know how to do these problems from your review worksheet. And there's your note on 8.3.